We have a sample problem here. An AC circuit with a 450 ohm resistor, 1.7 Henry inductor, and a 10 microfarad capacitor oscillates at a frequency of 50 hertz. If the source voltage is 220 volts RMS, answer the following questions. What is the RMS current in the circuit? What is the max voltage across the resistor? What is the average power dissipated by the resistor? All right, so our source voltage is alternating. We're given the RMS value, so 220 volts, and the frequency of 50 hertz. We're connected to a resistor, an inductor, and a capacitor. And I'm going to have to come back a little weird since I drew that kind of funny. So our resistor, 450 ohms, inductor, 1.7 Henry, capacitor, 10 microfarads. So question A, we want the RMS current in the circuit. If I look at the test notes, for the RLC circuit, I see that I, the peak or maximum current in this RLC circuit, will be the peak voltage over Z. Now we're given RMS voltage and we want RMS current. Well, the RMS voltage would be the max voltage over the square root of 2. The RMS current would be the max current over the square root of 2. So if I come to this equation and divide both sides by the square root of 2, this is actually now IRMS for this RLC circuit. This Z is still the impedance. So to solve for I, we need to find the impedance. Now you can make this one big calculation, but I do highly recommend finding XL and XC and then plugging them in, just to make sure you're getting something that kind of makes sense. XL, we know, is omega times L. We're not given omega, we're given frequency, but omega is just 2 pi f. So we would have 2 pi times the 50 hertz, that is omega. Now we multiply by the L, and that will give us our X sub L. So 2 pi times 50 times 1.7. I'm getting 534.07, and it keeps going. I'll round it to there though. So that's just a couple extra decimal places past. So XL, 534. XC, this is the one that's most commonly miscalculated. It's another reason why I suggest finding these separately so you can kind of make sense of what you're getting for them individually. So here, 1 over omega we know is 2 pi f. F is 50 hertz. C is 10 microfarads. I do want to put the 10 to the negative 6 in for micro. So 2 pi 10 exponent negative 6. I'm getting 318.31 ohms. So XC here is 318.31. Again, XC is the one that is most commonly miscalculated, so just be careful when you are calculating. Z then, the overall impedance, the R squared plus this quantity of XL minus XC, well, our resistor we know is 450, plus this quantity, XL we've calculated, XC we've calculated. That quantity needs to be squared. So let's go ahead and put this in, plus the quantity squared. I'm getting 499.05 ohms. So approximately 500 ohms. This circuit with this specific resistor, inductor, or capacitor oscillating at a frequency of 50 hertz has an overall ohms, kind of overall resistance of sorts, of 499 ohms. That's bigger than R, the actual resistor. The overall current then can be calculated by relating these ohms to the source voltage. Again, we've already divided by the square root of 2 on both sides so that our equation is RMS. The problem gave us the source voltage is 220 volts RMS. We've now calculated the overall impedance, the overall ohms. So I'm getting 0.4408 amps. So the IRMS in this circuit is 0.44 amps. The problem itself gives me at best 2 sig figs. So that's what I will round my answer to. In the next 2 steps though, I'm going to use this answer that has a few more digits just to minimize rounding error. Okay, so the current versus voltage in an RLC circuit, we always want to use Z, the impedance. Part B here, we want the maximum voltage across the resistor. If we go back to the line in the test notes that has just the resistor, we know that I through the resistor is equal to the voltage V sub R, the maximum voltage across the resistor, divided by the resistance. So the peak voltage across the resistor will be the peak current that flows through it times its resistance. Well, we don't know the peak current. We do happen to know the RMS current, and we know the relationship between peak and RMS. The current through the resistor is the same as the current that flows through the whole circuit. IR is IRLC in this case because the resistor is in series. All these elements are connected in series, so they all have the same peak value of current. Okay, since we want the maximum voltage, but I have RMS current, I can multiply RMS by the square root of 2 to get the peak current, then multiply by our resistance, and we will have this peak voltage. So square root of 2 times this 0.4408 times the resistor specifically is the 450 ohms. So that times the square root of 2 times 450, I'm getting to 2 sig figs, 280 volts. That would be the peak voltage the resistor would experience or see, the amplitude of the voltage across the resistor. we could easily find the peak voltage across any element. Right? The peak voltage across the inductor would be the peak current in this circuit times the inductive reactance. The peak voltage across the capacitor would be the peak current times the capacitive reactance. So we can go back to any of them individually to look at their voltages. Finally, part C, we want to know the average power dissipated by the resistor. Power for the resistor. When I look at this on the test notes, there's a whole bunch of equations going across. What's power of a resistor is equal to a number of different equations. I'm going to just go ahead and pick the easiest one in my mind. For a resistor, I know power is I squared R. That does need to specifically be the IRMS value, which we happen to have. So 0.4408 squared, and resistor, not Z. We want the actual resistance value, so the 450. So let me plug this in. Getting 87 watts. This is an average power because of the RMS current. The RMS value is relating directly to the average power value. So even though there's a whole bunch of equations, this approach hopefully is making sense. We always typically want to find Z if we're looking to relate current and voltage, because that's how they're related if we have all three elements. And then we can look at the individual elements once we get the current in the circuit.